So you'll see that I'm just finishing up my experiment here, varying the length of the string. I'm down here at the shortest length, and you'll notice that it's going quite rapidly, almost too rapid for me to time correctly. So we have to get creative sometimes when we're taking our data. Can you think of a good way to take data that does not involve me starting and stopping the timer very quickly? And instead of counting one period, I counted 3 periods. Um, so now I have a data point, 1.93. I would then have to divide that by 3 because this is the time for 3 periods. I want the time for 1 period, and then I can go from there. And that's indeed what I did. You have to get creative with your data and think carefully about how to take it in the most precise and objective way. All right, so here you can see the data that I have. I've made some notes over my data tables. For the angle of release, I was keeping the length constant and the mass constant. I only want to vary one independent variable at a time, so I was varying the angle. I released it at these angles, and here was my period. You can see there are some slight deviations. It seems to go down, but then it goes back up again. So if we look at this very carefully, we can say, okay, maybe the angle of release doesn't have an effect on the period. Maybe the period is actually not affected by the angle of release. If we look down here where I was measuring and changing the mass of the bob, either larger or smaller, and I was taking data about how that affected the period, we can probably look at this data and see, yeah, there are some fluctuations. It goes down and back up, but there does not seem to be anything significant. Let's look at this last set of data that I took. The last hypothesis I was testing, does the length of the string affect the period? The length of the string is my independent variable. The period is my dependent. It may depend upon the length of the string. That's what I'm testing. An experiment is a hypothesis test. I made notes about what I kept constant, constant angle, constant mass, and I varied the length of the string. As you can see here, I was measuring the shortest. I also measured it at the longest. And you can see the data here, and it seems like there's a relationship, does it not? For the longest length, we got the longest period. And every time we decrease the length of string, the period keeps decreasing as well. So isn't that interesting? Maybe there is a relationship there. But how can we know for sure? Is there a better way than just glancing at numbers to test to see if there is a relationship? And what does it mean that variables are related to each other, that they do have a relationship? Are there different types of relationships? That's what we're about to explore next. We're going to look at a better way of analyzing this data rather than just glancing at numbers in a graph. And hopefully you guys know the best way of doing this and finding relationships between variables. Remember, that's the whole point of this experiment. The question we were asking was, how can we change the period of a pendulum system? We tested these 3 hypotheses. We're looking for if-then relationships. We're looking to model a relationship between variables. We said that we thought there was no relationship between angle and period, nor between the mass of the bob and the period, but we suspected from the data we did seem to see a relationship. The shorter the length of the string, the shorter the period. So we want to show that in a better, more mathematical, more visual way. And so we can make some graphs. Desmos.com, desmos.com is a great graphing tool. It allows you to do several things. Right here you can see I have a little data table that matches the data of our first experiment. I just copied it over. I went to this little plus button, I added a table, and I inputted the numbers there. And you can see that the graph automatically plots them. And we can even go over here to the settings of the graph and add a label. The x-axis was angle of release. You always want to put a title for your axis and the measurement. What unit did you measure it in? And the y-axis, I believe, was the period of the pendulum, and that was measured in seconds. So we have right here our graph. Perfect. You can see I've kind of scaled it to see my data points here pretty well. And from this graph, we can see right away there is no relationship. As the angle of release goes up, what happens to the period of the pendulum here on the y-axis? It stays at a constant 1.6, 1.7. So that has no effect. Let's go to the next graph. The mass of the bob. You can see here I did the same thing. Mass on the x-axis, period time on the y-axis. And while this time there are some fluctuations, it seems like as the mass increases, the period does not change to any significant extent. It stays at around 1.6, 1.7 once again. So for these, we would say there is no relationship. And that's pretty simple to see visually with the graph. Let's make it more complicated and start looking at the length of the string. Let me take the time to label these axes. So you can see I have string length on the x-axis, period on the y-axis, and there are several interesting things that we can say about this. As the string length increases, as you go right on the x-axis, what happens to the values on the y-axis, to the period values? Well, they increase as well, right? So this is called a direct relationship. As one thing goes up, the other thing goes up as well. So yeah, we seem to have found a pretty interesting relationship between the length of the string and the period of a pendulum. We can be even more specific though and see if we can fit this data to a function, to an equation, see if we can make a line fit this data. Now, whenever we're trying to show a relationship like this type of graph is best. This is called a scatter plot because the points are scattered along the graph. You just place a dot at each point. And when you're trying to find a relationship on a scatter plot, it is always very tempting to take your pencil or whatever and just play a game of connect the dots and go from one dot to the next. In reality, though, we want a smooth, continuous function that that does not play connect the dots, but that is rather what we call the best fit. So I'm going to try some fits here, and you guys can follow along with me. Let's look over here on the left. This is where I inputted my data, the x values, that was length of the string, the y values, that was period in seconds. I'm going to see if this data fits a linear relationship, if there's a linear fit to this data. So what I've done here is I've said, okay, computer, see if these y values are proportional to the x values times a constant, and then plus a number, plus a y-intercept. You'll recognize this, I hope. Y equals mx plus b. That is the classic linear function. It's a line whenever you are graphing. The fact that I put this little tilde here, that means, okay, computer, you work out the relationship, you make the line for me. And whenever I plot that, you'll notice that the computer did not go and connect the dots, but rather it drew a best fit line, the line that best shows the relationship that it found between the data points. You can see that usually lines of best fit, if you're trying to draw it on a piece of paper and not on a computer like this, you typically want it to go straight through your data points, kind of averaging it out. It averages out, smooths out error for us. And you always want to try to get the same number of points to fall below the line that fall above it. So here you can see I have 1, 2, 3 data points falling below it, and I have 1, 2, 3 data points kind of falling above it. So this looks like a pretty good line of best fit. Yay, Desmos.com, great job. And you can see that it spits out some numbers over here. I want to look down here at the parameters. That's my M value, 1.53, goes right here. And the B value right here. These are very, very important in terms of graphing, and it's important to me that everyone starting this course understands what this equation means and how it works. This M value is what we refer to as the slope of the line. The slope of the line is basically how steep does the line rise and in what direction does it go. This is a positive value, which tells me that as my x value goes up, the y value also goes up. That's what a positive M, or a positive slope, means. That shows a direct relationship. One goes up, the other goes up. The value of this, the number associated with it, kind of shows you how they're related, the steepness of the line, if you will. This is a value of 1.53, so that's not too steep. What this really means is that for every one rise in the x value, the y value goes up 1.53644. So if we go over 1, the y value will go up about 1.5. If we go over 1, the y value will go up about 1.5. And that is how it works. The slope is defined as rise over run. How far up do you go divided by how far over do you go? Rise over run. It's a relationship between the y's and the x's. These statistic numbers right here are interesting, the r and the r squared. They're a little bit complicated, but all you need to know right now is that they show you how well this line of best fit really fits the data. Is it really a line of best fit, or is it just a line of okay fit? And the closer these are to 1, the better your line is. So you can see this is a pretty good line. This relationship is pretty valid. 0.989, 0.994. That's a pretty dang good relationship.